Hi everyone, my name is Thai. I work at the UIUC Research Center in Singapore, and today I will present our work on inter-theory dependency analysis for SMT string solvers. This is a joint work with Duc-Hiep and Joxan from National University of Singapore. In this talk, I am interested in the problem of inter-theory dependency. To describe it, let's look at the following example where we have a conjunction between the two constraints, a string equation and the length constraint. We have two constraints belonging to the two theories, string and integer. The two constraints depend on each other since they share common variables x, t, and u. So by dependency, I mean they share common variables. The problem is that although we can find the satisfying assignment for a variable in one constraint, for example x in a string equation, it's possible that the assignment doesn't satisfy the length constraint. Therefore, the search algorithm to find the solution becomes less efficient because it needs to backtrack in such case. And by inter-theory, I mean they belong to different theories. So in this work, we are interested in multi-shorted constraint language. The problem is not only fundamental, but also practical. For example, solving string equation and length constraints is well motivated by the security analysis of web applications. Here, the constraint language of interest includes string equations such as x is equal to the concatenation between y and z, length constraints such as the one to relate the length of x with the length of y and z, membership predicates such as x in R star, where R is the regular expression, and high-level string operations such as contains, index of. There are two main challenges. First of all, breaking the inter-theory dependency is not easy. To illustrate, let's look at the following satisfiability problems. For the satisfiability problem of string equations and length constraint, the desirability is unknown, while for the satisfiability problem of string equations, length constraint, and also extended string constraints such as replace, it is undecidable. In short, the dissatisfiability problem for string constraint is very hard. The second challenge comes from the typical design of SMT solvers. Specifically, each theory solver usually works independently from the other solver. Because of the unavoidable inter-theory interactions between constraints from different theories, it becomes harder to deal with inter-theory dependency, and the implementation of our technique also becomes more challenging. As you can see in the title, we have two main contributions, the inter-theory dependency analysis and its implementation inside an SMT string solver. The key idea of our analysis is based on the so-called solved form. Intuitively, it is an SSA-like form. For example, the formula x is equal to t and x is in solved form with respect to x, so we can easily find a satisfying assignment for x based on the assignments for t and x. I don't want to go into the formal definition of the solved form, which is a bit more complicated. I would like to refer to our paper for more precise definition and more illustrative examples. Instead, I would like to explain here how it is useful in breaking the inter-theory dependency. Let's look at the following example. Here, we have two constraints, x, y, z is equal to t, u, w, and 2x is equal to 2t plus 3u. To proceed, a typical way is to apply the case-splitting rule based on the relative relationship between between the length of x and the length of t, so that the formula is in solved form with respect to x in the left branch, or an inconsistency is detected between the length constraint in the right branch. Specifically, in the right branch, we have conflict between 2x is equal to 2t plus 3u and the length of x is less than length of t. In short, the solved form has either simplified string equation and length constraints or be able to learn a better conflict clause. Based on the solved form, we next introduce the solved form distance in order to measure the number of steps required to break the dependency. As you can see in the previous slide, each solved form is defined with respect to some variable x. Now each variable is also assigned with some priority value, which is computed based on the number of length and extended constraints where the variable appears. This allows us to prioritize the variable that help us resolve the largest number of length and extended constraints, or otherwise, if it contradicts with length and extended constraints, we can learn a better conflict clause which involves these constraints from different theories. We define the solved form distance for a string equation E by locally constructing a derivation tree for it. Later it will be clearer why we only need to focus on string equations. In a figure, suppose after two applications of the splitting rule, we can obtain a formula h in solved form with respect to x, which is the variable of highest priority. Then the solved form distance is 2. So intuitively, we just count the number of branching points in a derivation tree. You can find the formal definition of the solved form distance in the paper, where we define it as a tuple whose size is the same as the number of variables, and it is defined recursively for each node based on the solved form distances for each child nodes. So the solved form distance for the string equation E is simply the one for the root node. I have just introduced the solved form and the solved form distance. Now I describe how we build the inter-theory dependency analysis. Basically, we would like to construct an order for string equations. In this order, we prioritize the equation which can be reduced most quickly into a formula in solved form with respect to its set of variables. We also need to assign the priority value for each variable so that it reflects how much the inter-theory dependency between string equation and length constraint and also extended string constraint is. Suppose we have two string equations f and g. We will construct a binary relations for f and g based on the whole set of variables v, which is the superset of both the variables of f and g. The comparison operator is also based on the priority map m, that is the map from the set of variables v to the natural number set. This is to represent the number of length and extended constraint where each variable appears. So a string equation is given higher priority to be solved if its solved form distance with respect to v and m is smaller. The second task is to track the decisions that we have made. If we look back to the derivation tree for each string equation, we can see that each branch is guarded by a Boolean variable. So we will collect all the decisions we made. In other words, the Boolean value that is assigned for each variable in order to obtain the corresponding distance. We call such list a decision witness. This is really helpful because it enables us to replay these solving steps later in a global context. Note that in the figure, we have built a local derivation tree for an equation E. Now in a global context, we simply choose the correct decision to follow the path we want. For example, the leftmost branch will lead to the formula h in solved form with respect to x. Now I will discuss how we implement the analysis inside an SMT solver. In our implementation, we use the Z3 solver, but the technique is also applicable to other SMT solvers. In the figure, I show the main components of Z3, which contains a congruence closure core, a set solver, and multiple built-in theory solvers, such as b-vector, array, arithmetic, string. Z3 takes as input a formula and returns a set answer, an unset answer, or an unknown answer. Let's focus on the conjunction of string equation, length constraint, and extended string constraints. Length constraints will be handled by the integer theory solver. For string theory solver, we are able to collect a list of the string equation and a list of extended string constraints, so we can easily construct a partial order for string equations by using the priority queue data structure. Handling length and extended string constraint is similar to what had been done before in previous works. Next, we have to deal with the disjunctions that we are introducing when applying the case-splitting rule. As I said before, we will control the search order by assigning the Boolean value for decision variables. This allows us to control which branch we want to follow. For example, in the figure, if we assign the true value for E, then the search will follow the left branch. Otherwise, it will follow the right branch. This is done at the level of the set solver. Meanwhile, the handling of conjunction is done at the level of the string theory solvers. Okay, so now let's look at our experimental evaluation. We conducted 2 case studies. Both of them are also used by previous works in their evaluation. So it is easy for us to demonstrate the outperformance of our new solver compared with the state-of-the-art solvers. The first benchmark set is generated by simply executing JavaScript programs using a symbolic executor for JavaScript. Because its underlying string solver cannot handle extended string constraint, the input has been simplified and only contains string equation and length constraint. But don't worry, we will have another case study to cover this point. Here you can see that compared with the solvers which have similar number of solved instances, such as S3B CVC4 version 1.5 and CVC4 version 1.7, our solver is at least 8 times faster in the set category. For the unset category, the speedup is more than 3 times. Now, the second benchmark set comes from the symbolic execution of Python program using a symbolic executor for Python. As said, this benchmark set also contains extended string constraints such as index of contents. There are 2 subsets. One is generated with CVC4 as its underlying solver. The other is with Z3. Here we can also see a similar speedup. For the set benchmark, the speedup is over 10 times. For the unset benchmark, the speedup is not as marked. However, the important thing here is that the number of unsatisfiable benchmarks that our solver can handle is always more than the other solvers. The reason for the speedup in a set category is that we have better search strategy and able to find a solution faster. Meanwhile, for unset category, we focus more on the inter-theory conflicts and able to detect such conflict earlier. In both cases, the fact that we can learn better conflict clauses is also very helpful. To conclude my talk, let me summarize some important remarks. So I've just presented a sound inter-theory dependency analysis for an expressive language for string constraint. I also give a brief overview on how we implement it efficiently inside SMT solvers. Lastly, I showed the outperformance of our solver over state-of-the-art string solver by evaluating it with different benchmarks which are also used before. Since the inter-theory dependency is very fundamental problem, as a follow-up work, I would like to apply the analysis to handle more constraints with such kind of dependency. For example, in string domain, it can be created by string conversion operators. In other domains, such as sequences, sets, where the constraint language is also multi-sorted, we can also see similar applicability of our analysis. Our current implementation is based on an old version of the Z3 source code, so we plan to merge our code into the latest one of Z3 in the GitHub repository. And thank you for listening.